Good morning, everyone. It is Friday. It really doesn't matter. Every day is the same day anyway. All right, so today we're going to look at redox titrations and the Winkler method that uses redox titration. But before we do that, let's go back here. Kashmia mentioned to me that I made a mistake here, and I did. Where? Right here. Okay? I'm supposed to multiply 5 to this whole equation so this 5 can cancel. So, what I forgot to do was put a 5 right here. I'm sorry. Which means I need to put a 5 here as well. Thanks, Kashmia. I hope you guys weren't confused or anything, but here it is. Okay, now it's complete. Okay. Let's go back to what we're supposed to do today. All right, so before we look at titration, let's take a look at ozone and chlorine. Now, there's one similarity between the two chemicals is that they're both disinfectant, very good disinfectant towards microbial and other what we call germ-living creature. Now, how do they do that? Well, they are good oxidizing agent. Now, what are oxidizing agent? These are chemicals that cause another chemical to oxidize. So ozone and chlorine are good oxidizing agent because they will cause certain chemical to, gain an oxygen, lose hydrogen, and most importantly, losing electrons. Okay? Because of that, that's a good microbial killing ability. Now, chlorine. When you use chlorine as a disinfectant, it can be any of these forms. All right? Any of those forms. The main reason of using chlorine, of course, is to kill bacteria. Now, don't use too much because this may arrive. Okay, and that's toxic. So if you're chlorinating your swimming pool because you're rich and you have one of those in your backyard, you don't mind the maintenance, don't use too much chlorine. And you don't want to have a huge buildup of chloroform. That can be disastrous. Now, ozone. Ozone actually has virus killing ability. Hey, maybe we can throw these COVID-19 up into the ozone layer and there you go, bye. I'm only kidding. That's not sure that's gonna work. Anyway, you can go through this chart and see what chlorine and ozone do and its physical property and stuff like that. But let's get back to the main topics. Redox titration. Now, we know how to do regular titration, regular acid and base titration. Redox titration is really the same thing. The only difference, of course, is that you have different indicator, you'll have different titrant. You still use a burette. Okay, the setup is very similar. Some of you already know that because you're doing that for your IA. But the calculation-wise, it's not that much of a difference. Now, let's take a look at this question. This question requires the finding of iron 2+. I want to know how much iron 2+ there are in moles if this amount of permanganate was used. So let's set up this question. So I have 0.02118 molarity of permanganate at 0.1 liters. I want to know how many mole is that for iron 2 sulfate, which is really iron 2+. All right. Hey, you're not just going to straight up and do this, are you? You really think that iron and permanganate is 1-to-1? No, I'm afraid not. You're going to have to balance this. Redox balance it. Split this into 2 halves and treat 2 halves. You know the idea. But I took the liberty and did this for you. So here it is. This is the balanced version of this reaction under acidic condition. You know that's important. Because under basic condition, things will look a little different. Here you go. Okay, there's your redox balance reaction. So still, you're looking for the amount of mole of this. And what you did is that you took this molarity of permanganate at this volume. What would be the mole of iron 2 plus? Okay. Hey, stoichiometry. Seems like this never goes away. So you have moles per liter of manganese permanganate. Permanganate. At 0.1 liter, so liters cancel. The mole ratio here is that for every mole of permanganate, it's really 5 mole of iron 2 plus. Permanganate cancel, mole cancel, and crunching this into my calculator, I have 0.01059 mole. There you go. So the trick here is that balance redoxly and then put in the numbers and do exactly what you've been doing with stoichiometry. Simple, huh? But in reality, this is a lot of work. Okay? Especially trying to do this in a lab. So the 6 of you who did redox reaction in your IA already know that it's not that easy to pinpoint that endpoint in a redox reaction. So I have an example for you, and this is called a Winkler method. Now the Winkler method is an excellent method used today to find out how much oxygen is in a sample of water, or how much CO2 is in a sample of water. But we're going to put our attention towards oxygen. Now, why is that important? Because if there's a lot of oxygen in water, life in water will be very happy. Fish is an animal. They too breathe oxygen for aerobic respiration. Without oxygen, they're going to be in a lot of trouble. You'll notice that they tend to float more to the surface to capture oxygen that way. So if you have an aquarium tank and you'll notice that your fish is always at the surface, I think there's a very small amount of dissolved oxygen in that water. You might want to get a pump or plant more, water plant or something. Now, let's go back to the chemistry here. Oxygen is nonpolar. Water is polar. Polar and nonpolar doesn't really come together that easily. Okay, so trying to put oxygen in water, it's a complicated task, but it can be done. Now, one way to have it done easier is by playing around with temperature. Basically, the higher the temperature, the lower the solubility. What that means is that if your water is colder, you'll notice that there's more oxygen in there. More oxygen, you have a healthy ecosystem. Your fish is going to thank you. Okay, your fish is going to thank you. Okay, now let's take a look at what the Wenkler method do. Now, the Winkler method is used to calculate the amount of dissolved oxygen in water. Okay? You do your experiment to discover that number. Now, through this number, one more thing can be found. And that is this thing called BOD, biochemical oxygen demand. The higher this number, the more polluted your water. So, government around the world, when they do water testing, they test for BOD. And we're going to do a question involving BOD. Okay? It's related, of course, to dissolved oxygen using the Winkler method. Now, the amount of oxygen dissolved in water, or the amount of BOD, is actually a very, 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 very tiny number. So, because it's tiny, we express this concentration through ppm, parts per million. Okay? So, let's take a look at the chemistry behind this. So, in the Winkler method, it's actually a 5-day process. You will try to discover what the dissolved oxygen is on day 1, and 5 days later you'll do the same procedure and see what the dissolved oxygen may be, and by that you can see the difference in terms of dissolved oxygen in your water. Okay, if the water is very polluted, you can calculate for the amount of BOD that exists. And again, we'll see that in the next question. Okay, this has to be in the dark. All right, so let's take a look at the chemical process. This is a 4-step chemical process. Step 1, 2, 3, and 4. Okay, step 2 is the most important because this is the step that oxygen in the water is reacted, okay, with the manganese 2+. Now, the very detailed of this reaction, or what you're able to see, is the amount of bisulfate. Okay. Now, let's take a look at this reaction. Okay, let's take a look at this reaction. What you're looking for here is this number. If you're able to find the mole of this, you can use stoichiometry to find the mole of this. Now, with the mole of this, you can relate it to this I2 to get the mole of that. Using the mole of that, you can use stoichiometry to get the mole of this. Again, relating it to this reaction, this can relate to this. So at the end, you'll get the value of desired. Okay? Now, it's very difficult for me just to say it. So what I'm going to do is I'm going to do the next example and show you exactly how to do the math. And hopefully you understand it. Okay? So let's take a look at problem number 7. Sorry about that. I'm not sure why there are all these things here. Okay, but this is the Winkler method. So this question, you took 50 milliliters of water sample, took it from the pond, and you notice that 5.25 milliliter of 0.005 mole of thiosulfate was required to react with iodine. So let me say that again. It took 5.25 milliliter at 0.005 molar concentration of thiosulfate to react with iodine. Okay, that's a big clue here. Question A. Determine the concentration of dissolved oxygen in ppm of the water sample. So I want to know what is the ppm of oxygen given this. All right, let's go back to the last page. Okay, let's go back here. Let's zoom in to this reaction. So what they're saying is that here's thiosulfate, and you used 0.005 molar of this at 0.00525 liters. Okay? Can I use this information to find out what the mole of this be? Let's do it. Let me show you how this is done. Okay? So, I have 0.005 moles per liter of thiosulfate. And I have 0.00525 liters of it. So liters cancel. Now I have the moles of thiosulfate. With the mole of thiosulfate, I can use my stoichiometry to find out exactly how many mole of iodine gas. In this case, dissolved iodine. Moles cancel. Thiosulfate cancel. And this is the cool part. Now, what you have here is the mole of I2. This mole of I2 can be related to this mole of I2 and this mole. Let me show you what I mean. Okay, this and this. For every mole of I2 is equivalent to every mole of this chemical right here. Okay? Mole and mole cancel. I2 and I2 cancel. Now, we're going to do the same thing, because for this individual, you can relate to this one and this one. Hey, this is your desire. This is what you want. So you would finish this by saying that for every 2 mole of this guy is a mole of oxygen. Mole and mole cancel. That cancel. And you will get an answer here. Let me calculate this. My calculator. You will get 6.56 times 10 to the power of -6 mole of oxygen gas. Hopefully you know where my numbers are coming from. All right, let's go back to the first question. Okay, we can do question A now. We want to know, what is the concentration of oxygen in ppm for this water sample? So, oxygen. We just calculate the mole of oxygen. So, let's do this. So, question A. Okay, we know that there's 6.56 times 10 to the -6 mole of oxygen. Okay, in 0.05 liters of water. So if you were to divide that, that would be the molarity of oxygen gas in this amount of water. All right? Now, I don't want molarity. I want ppm. So how am I going to change molarity to ppm? Well, we need to know that ppm is milligram per liter. Liter is fine. We just need to change mole here to milligram. Well, hopefully you remember how to do that. To change moles to gram, we need molar mass, because every 32 grams of oxygen is 1 mole. So mole will cancel. Now we change grams to milligrams. Well, we know that every gram is 1,000 milligram. Okay, now we have ppm. And by doing the math here, Okay, 4.2 ppm. Okay, what does this mean? The dissolved oxygen concentration in 50 milliliters of water was 4.2 ppm. Okay, that's the concentration of oxygen in 50 milliliters of water. Okay, after doing the experiment, using these data, that's what we found out. Now, what does this 4.2 ppm of dissolved oxygen mean? Is the water clean? Is it good for my fish to live? Well, let's do question B now. Because question B is asking me for BOD. Okay? Biochemical oxygen demand. Now, let's read the question. Deduce the BOD in ppm of the water sample, assuming that the maximum solubility of oxygen in water is actually 9 ppm. So, at room temperature, because we're assuming that this water is at room temperature, okay? The maximum solubility of oxygen, so the maximum dissolved oxygen is actually 9. You cannot go over 9. Okay? If it was above 9, this number temperature should have been lower. But at room temperature, it was 9. And I want to know what BOD is. Okay? It's actually very simple to do. Okay? So if the maximum is 9, and experimentally, we figured out that the dissolved oxygen was 4.2. What's left is your BOD. Okay? So I might want you to think about that. Okay, so BOD is taking the maximum dissolved oxygen at a certain temperature, and you subtract that by the amount that was experimentally discovered. Okay, so basically, 9 ppm is what you, I guess, investigated on day 0 when you collected this water. 5 days later, you notice that your dissolved oxygen is 4.2. Now you're probably wondering, oh, well, what happened to those oxygen? Why did it go down? Well, the assumption is that there's life in water. Okay, and they need to breathe. All right? And I guess they took 4.8 ppm in that amount of 5 days. So that's how you calculate BOD. Now, there's still a hidden question here. C, 4.8 ppm in BOD. Does that mean your water is polluted? Well, this is the part where you're going to have to do a little bit of research. From what I discovered is that sewer, a nasty place. If you take the BOD of sewage water, the BOD can range from 100 to 400 ppm. Hey, you only have 4.8 ppm. Not polluted at all. I would drink from it. No, I'm sure. I'm kidding, I won't. But compared to sewage water, which can range from 100 to 400, 4.8, that's not that bad. All right, so that is the Winkler method. That's exactly how you would do one of these questions through force redox titration. So I was really trying to find out what the mole of this is. If you find the mole of this, think about it. If you have the mole of that, just divide it by 4. And you will get the mole of this. With the mole of that, divide that by the sample of water that you use. You'll get molarity. Change that to ppm, which is the standard for BOD. And you'll find out how much dissolved oxygen is in your sample of water. Okay? So, hopefully this helps. I would assume that you'll do some reading regarding the Winkler method on Cognity. I will assign some reading next week. All right. If there's any questions, hey, make sure to send me some message on Google Classroom or my email. And that's it for today. Okay, so next week we'll start 9.2, which is on building voltaic cell and electrolytic cell. And that should be fun. There's not much calculation involved there. And let's call it the day. Let's call it the week. Right? Enjoy your weekend. Bye now.